Something that I struggled with understanding is S Stereochemistry. This appeared on the second exam a lot, and then it also appeared again on the third exam, which I will show later, which is why it is important for me to understand now in order to be successful in the final. So the first part of understanding S Stereochemistry is understanding chirality. A chiral molecule will have an asymmetric or chiral center, which the most common type of this is a tetrahedral atom with 4 different bonded groups. In all of my examples that I will be doing today, I'll be using carbon molecule as the center. They have a lack of a plane of symmetry, which means that chiral molecules, you can't cut in half and have 2 mirror images on each side. You'll have 2 different sides based on priorities. And then also, chiral molecules are non-superimposable, while achiral molecules are superimposable, which means you can't lie one chiral molecule over the other and have the same exact thing, but you could do that with an achiral molecule. The best way of describing this is placing your left hand over your right hand. Obviously those aren't the 2 same things, so in essence your hands are chiral. The next part of understanding this is understanding enantiomers. So an enantiomer is a non-superimposable mirror image of another molecule. So if you were to take a molecule and rotate it 180 degrees like so, then it would be mirror images of each other like this. Enantiomers also have the same physical properties, such as density, melting point, and boiling point. And an important way of representing these is with a 3D representation using hashed, wedged, and normal bonds to define how the bonded groups go into and out of and in the plane of the page. And the 2 different types of mirror images will define the RNS stereochemical molecules. So in order to define the RNS, you have to understand the Kohn-Ingle pre-log rules. The first one says that the highest priority will have the highest atomic number. For the same atomic number, then the atomic mass will break the tie. The attached groups, whichever one has the highest atomic number, will have the higher priority. And for multiple bonds, the multiple bonds become multiplied bonds, so a double bond will be bonded to more than 1 carbon because there's a double bond, and this will give it a higher priority than, say, a single bond. So now I have some examples to demonstrate these rules. Just for time's sake, I went ahead and prioritized them. So on this first molecule, the Br has the highest priority because it has the highest atomic number. The ethyl group has the second highest priority because at the point of difference, so here and here, these are both carbon atoms, but if you were to continue on, this is bonded to hydrogen while this is bonded to another carbon, and carbon has a higher atomic number than hydrogen does. So this takes second priority, this takes third, hydrogen takes fourth with the lowest atomic number. On this molecule, oxygen has the highest atomic number, so that takes first priority. On these 2, the point of difference is hydrogen and oxygen. Oxygen has the higher atomic number than hydrogen, so this takes second priority, this takes third, and this takes fourth. And on here, the reason there's no priorities is because this is actually an achiral molecule. As I said earlier, in order to define a chiral molecule, there have to be 4 different bonded groups, and on this there are 2 hydrogens, so this is achiral. So now, in order to define if these are RNS, you take the lowest priority and point it away from you, and then depending on how it goes from 1 to 2 to 3, if it is clockwise, then it is R. If it is counterclockwise, then it is S. That is with the lowest priority group pointing away from you. This is hard for me to understand on paper, so another rule that is helpful is using the right hand rule. So if you point your thumb up along the lowest priority group and then curl it from 1 to 2 to 3, and it works like that with your right hand, then it is R. If you go from 1 to 2 to 3 with your left hand, then it is S. This was still difficult for me to understand because I couldn't figure out how to arrange my hands to understand RNS. So I found a trick that works best for me, and it is called the red, white, and blue trick. So the way that the red, white, and blue trick works is first by placing the lowest priority group in the back, and that is the green one, and then the rest from 1 to 2 to 3, it goes red, white, blue. So first priority is bromine, that's up. Second, white is this ethyl group, and then the third is the methyl group. And then you go from red to white to blue. So since we are going counterclockwise, this is S. Over here, the same thing applies. This one also happens to be S, so hydrogen is in the back. The third one is in the top. The first one is here, OH. Second is over here. So then going from red to white to blue, it is again going counterclockwise, which also makes this S. So this trick has really helped me understand how to put these molecules in space in order to understand if they are R and S. So this is important understanding because this is a question taken from exam 3 that says, which of the following best describes stereochemical outcome of the product of the following substitution reaction? And all of the answer choices on this question had R or S within the answers, so it is really important to not understand this kind of substitution reaction, but to understand the product of it and the stereochemical shape of it, which involve R and S. So this relates back to understanding substitution between SN1, SN2, E1, and E2, which are also things that I struggle with, but it makes it easier knowing that I understand R and S enantiomers, and I think that this will help me be successful on the final.